Howdy, everybody. I hope wherever you are or whenever you are, you're having a great time and everything's going well with you. I'm back at it. We're here doing Advent of Code Day 17, more of the Intcode work. Um, for me, it's been a little while, so I'm just going to try and do a little bit of review to make sure everyone knows what's going on. But if you're watching this stuff in series in the future sometime, you may not see that, but it has been a while for me. I'm sorry. I've been busy with life and stuff like that, and I just haven't set aside the time, and that's what I really need to be better about, is setting aside the time to do this stuff, because I enjoy it. It's fun for me to solve these problems, and it's fun for me to share the stuff that I learn. Hopefully it's helpful to you, right? I probably have said this before. I really enjoy teaching. I'm not necessarily the best teacher. Obviously, my teaching you depends on whether you enjoy it or not, right? So, but I enjoy doing it nonetheless, so I'll probably keep doing this. I just need to dedicate some more time to doing it. With that being said, let's talk about Intcode programming, right? Again, I should say Intcode Computer. I'll try and get my terminology straight here. If you haven't been following along or took a break like I did, what we've been working on is the idea of an Intcode computer. We're creating our own quote unquote computer, right, that can be given a program, an Intcode program, right? So it gives you a set of instructions to run, much like a machine language or a very low level, program. It will give you instructions that it wants you to do. Add two numbers, multiply two numbers, move this number here, get this input, set this output, those type of things. And then those instructions turn into programs. And in the previous videos, you've seen you can actually do really cool things with just a small set of instructions, right? And today's day is not much different than that, right? We already have built our Intcode computer, and so it's going to now give us a program that we can run on that computer to do some really cool stuff. And that's why I was showing you the vacuum robot in space AI generated image for the thumbnail of this thing. You're gonna take a vacuum, and it's going to go through it's not really a maze. It's like scaffolding that it needs to follow. And the goal of the thing is, can you get it to go through all of the scaffolding and get some output? So it actually doesn't, we don't really change our Intcode computer in this code, if I remember correctly. All the instructions are already there, so we don't have to do anything with it. It's just a question of how do you interact with your Intcode computer, right? Yeah, you think about the computer you have at your desk or your table or wherever. It's a computer, but you type, you move the mouse as input. Maybe you give it a program to run, and then you get output on your screen, right? So I've got OBS recording stuff. You go to a web browser, you type in something, and there you get a web page, right? The question is how do you do that interaction with your Intcode computer? And again, it's very simplistic, I guess, is what we're doing. We're at least for today, we're doing ASCII, which is just text, right? We're going to give it input, and it's going to spit out output as text, and then we can display that output. That's pretty simple, but that is not much different, right? Is you're just adding some layer of complexity to that basic input output. When you think about how does a computer screen work, how with a video card, right? How does a keyboard work with your USB controller in your computer, right? Those things all are doing input-output routines, interacting with programs, interacting with your processor to produce input and receive output. And so we'll kind of talk about the two potential ways that you solve that problem, at least from a programming perspective, namely threading. Can we use threads and locking and synchronization to interact with different inputs and outputs? And then we'll go on to the one that we've been working on recently, which is asynchronous programming, where we use awaits and things like that, and selecting on those asynchronous things to work on stuff, which we've talked about before. So I'll just do a really high level review of those things, and I drew a couple diagrams to kind of refresh it in my mind that we'll look at. But given that, let's move on and let's talk about the problem for the day, right? So there's an early warning system. It detected a solar flare, and the shield's gone up, but it's cut off some of the Wi-Fi for the small robots, and so we have a bunch of robots running around the ship. They're not aware of what's going to happen, but you do have access to a small vacuum robot that is at its charging station, and it has some wired cameras that outside, not the robot, but there are wired cameras outside where you can kind of see what this vacuum robot is doing. And so the idea is you're going to see a map of this robot, and you want to be able to go through all of the scaffolding of the robot. So your input is going to be the Intcode program that's going to run on your Intcode computer, and it's called the Aft Scaffolding Control Information Interface, ASCII for short, right? ASCII. So it's going to spit out the map of the thing of what the camera is seeing, and then you're going to be able to give it instructions in part 2 to tell the robot how to move. But for part 1, it's just going to it's going to spit out the initial map, and you're going to want to look at that map and see what it is. And so you can see the periods are empty space, and the hashes are the scaffolding, and these arrows will change, but they'll be the position of the robot wherever it is on the scaffolding until it falls, right? And what it's asking you to do for part 1 is take this map and find all the intersections of the scaffolding. That is where there's a complete intersection of the scaffolding, and count those up. And the way that you count them up is you take their XY coordinates of each of the intersections and you multiply them together. So for example, this is an intersection. It's at 2, 2 on the map. So it has a value of 4. This one is at 2, 4 on the map. So it has a value of 8. You multiply the X and Y coordinates together to get 8, right? And you just do that for all of them, sum it up, and you get to your answer. So I think part 1 is really just can you read the output of your program and get the results of the intersections and produce that as your output. That's kind of just like, you can think about it as like an initial step to the actual part 2. And I'll talk about part 2 really quick, and then we'll get on to the solutions and stuff like that so you can see what's going on. For part 2, what it says is now that you've kind of seen the map, you're going to do this interaction with the computer program, the Intcode program on your computer. It will print out the initial map, and then you will give it a list of instructions on how to move the robot. And it kind of gives you this like limited way of doing it. It says you have 1 movement routine and 3 movement functions, A, B, or C. And each of them have a finite amount of space. So you can't just look at the thing. You can't just look at the solution they give you this map right here. You can't just say, here's what I want you to do. Here's the whole thing. It's limited space. And so they want you to find like patterns within the optimal movement of the robot to visit all of the scaffolding, right? And you have 3 subroutines. You can think about them as just 3 functions of movements that your robot that you will give it. And then you have a main function that kind of chains those together. And I think it does a pretty good of describing this, so I'll just show you how they solve it. But if you look at this, you can start to see patterns where you have an R4, R4, R8, and then you have an R4, R4, R8, and then you have R8, 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 right? You can see these patterns starting to form of like, here's similar things. And I should say is when you're looking at it, you have to think about where the robot is at the point in time. And it describes this pretty well. Notice this B routine right here and this B routine right here, up here in this corner, they don't really look the same, right? But if you think about what's happening is if you're going, if you're right at this position and you're facing this direction, right? So you're facing this way and it says go right and then go up 4 or go 4 after you turn right, it will push it up and then it will go 1, 2, 3, 4. And then you'll go right again and go 4, and then you'll go right again and go 8. Well, it turns out that same thing happens right here, right? If you're right here, even though you're facing a different direction this time, and so you turn 8, and now or you turn and you go 4, turn and go 8, turn and go 8. These happen to be like the same way to solve it, right? And so essentially what's happening is you're kind of looking for these patterns, and it can be kind of hard to look for them at first. I should say there's probably a programmatic way to do this. One solution that I thought of that I never actually implemented is using artificial intelligence, not like the ChatGPT AI, but like a more traditional computer science AI to like find the solution. I believe it's called generative. It is called generative AI, I think, because I think it's not generative. I don't know why I have it in my mind. I can't think of the specific AI. You feel free to tell me in the comments what AI it is. But the idea is you can get the AI to run multiple iterations to try and solve the problem, and it will just keep the AI will try and figure out the patterns for you, and once it figures it out, it will use that in future generations of the AI to like find solutions. And they've used this to solve things like, can you finish Super Mario Brothers, for example, right? For some reason I thought it was generative, but maybe that name has been stolen or something. I know I'm missing it. Anyway, I've thought of using AI to do this because it could potentially find it. You could also use just a general breadth first or depth first type search where you say, okay, well, I know all my intersection points, like, or all my turns, and can I just like, okay, what if I go here, here, and here? Can I use that pattern and other patterns to solve the problem? Those things would work too. The way I ended up solving this, though, what was in looking for these patterns was to create a GUI. And so that's why we're going to talk about using select so we can interact with our Intcode Computer and our GUI using a select statement, right? The alternative, which we'll talk about briefly, is you could use synchronization, like locking, to like lock those shared resources to do stuff. And so, but because I had a GUI, I could kind of then look at it like this and say, oh, here are the patterns I can see, and then I can just enter it into the thing until I figure out the right one. And you may argue, oh, you didn't solve it programmatically. I think I did. I built a GUI. Some people have different opinions of what it means to solve it programmatically, right? What came to mind just now is I helped someone solve a problem. I didn't really help them that much. There was just they were using Google Sheets to solve some of the Advent of Code stuff, which I thought was awesome. And they were using a cell that was cutting off some of the numbers, and so that's what the problem was. And so they were just asking for help. I happened to notice that it was like cutting off some of the numbers, I think is what it was. And they fixed it and it was cool. And I was like, that's really cool that you can solve these problems with Google Sheets. So I would say however you think you can solve it is very cool. There are people who use pen and paper, and I think that's an optimal solution. For our case, we already have an Intcode Computer, and I thought, why don't we use that? We'll create a GUI so we can visualize part 2 and walk through it until we find an actual solution. So that's what I did, right? But that's the problem, right? Is the idea is you're going to try and figure out, hey, how do I can only have these 3 subroutines and then one main routine that's going to like use them, right? So this one uses ABC, BAC, and that solves this map, right? And what will happen is if you've touched all of the scaffolding, you will eventually get a large number of like how much dust the robot collected, and that's the solution to your problem. So what you're going to do is look in the output as you're doing this thing. You're going to eventually get a number that's obviously out of ASCII range, and that will be the like solution to your problem, is what it is. So, but with that, let's talk about a little bit. Just review a little bit. Oh, I guess I'm already there. These two ideas of programming, right? So what are these two ways? Both of them use threads. I mean, technically the asynchronous doesn't need to, but they often will. But in this approach, which is sometimes called synchronous or a locking approach, right, is we have some kind of shared memory in the middle here, and we use mutexes, short form mutual exclusion, right? We use these mutexes to communicate. So on this left side, we have a thread that's running our Intcode program. And on the right side, we have the UI, right? In this case, it's a terminal UI, a TUI. And both of them are going to be receiving input and giving output, right? The TUI is going to output to the terminal. Our program's going to output ASCII characters, they're numbers, but we'll turn them into ASCII, and we need to put them somewhere, right? And in our case, the TUI wants to know what that is, right? So you can think about as we give the input some, or we give the program some input, it does some work on it, spits out some output, and then we want to give that to the TUI so that it can output it onto the screen, right? And then as we're typing, the TUI will generate events that will be used as input to the program. But there's a lot of shared memory here, right? You think about what the TUI is displaying as output is actually coming from the output of this program, right? And so if we have the TUI displaying the output and this updating the values of the output at the same time, you can get, contention. Race conditions can alter the memory in ways that can cause problems, right? So the way you solve that traditionally is with a mutex, as you say, whenever I'm writing output or I'm reading output, reading data for output, I should say, I'm going to lock that chunk of data so the other thread doesn't touch it. And I think we've talked about this before, so I won't go into much more detail than that. But it's the same thing with the input, right? Is the input, you click on the keyboard and you want that input to go in, but maybe the program isn't ready to receive input. You don't want to like stall and wait on that. So you have some kind of buffer here that is guarded by a mutex, and this thing pushes things on that buffer, and then when things are ready to read on this side, that's pushed in there. I did a very high level. We have just 2 threads here, but there's a potential for you to have multiple threads, right? You could have a thread for the event handling, a thread for the output on both sides. So you could easily have 4 or more threads, potentially even a one for here, right? So you could have lots of threads. They all are they all are in contention for using these resources, and you don't want to be overriding or accessing that data in the middle of a write or a change, and so you use mutexes to do that, okay? So this is the old model, and we did a couple initial implementations where we did that, right? As where we used this like synchronous approach with threads, but we've since moved over to, no, that's not it. File, open, load from file. We've changed to kind of using am I not going to find this? Using an asynchronous approach, right? And I have previous videos where we've talked about Tokyo and asynchronous programming in Rust. But just to remind you that, if you're familiar with JavaScript, you've probably used asynchronous programming for like fetching data from an API, for example. Maybe at a higher, more abstract level, you actually haven't had to use the asynchronous programming, but those tools use that. And I've seen a lot of people talk about, the pros and cons of asynchronous programming versus traditional methods, or just not threaded at all. But the general idea, I think is important to understand. Even if you're maybe not a fan of how Rust implemented it, I actually think they've done a fairly good job. A lot of the complaints I've seen of Rust's asynchronous programming kind of apply to all asynchronous programming. It's just that's the way asynchronous programming is. And it can be harder to wrap your mind around, and it can be harder to like, especially if you're used to, oh, I just create this lock and I watch those things, and I'm used to the synchronous programming. It can feel different, I guess is the best way to describe it. And so just give yourself some time to learn and understand about it. But how do we solve our problem in our solution, right? Is here again, we have some kind of TUI, and we have our Intcode computer that's going to be running. We want them to interact with each other, but we're going to try and do it, quote unquote, without locks. Under the hood, these select things may use locking technology. I actually don't think they do. But they potentially could. But underlying, we're using Tokyo's asynchronous runtime to solve it, right? And the idea is we'll have this program running in its own asynchronous pool, which is likely a thread. It's a green thread, right? Or like more like a Go routine, but it will be running, and it will just run until it's waiting for input, or the output is buffered and it can't spit any more output. And on the other side, you'll have the TUI as well, right? Is it will want to be like handling events and doing stuff like that, and all of that is kind of guarded by this select statement, where all of these, what I should say is the data is guarded by the select statement. So, the data is right here. I'm updating this on the fly. Sorry. Right, all the data is right here inside this select statement, and it's the select statement itself that's doing the like quote unquote locking of the data, right? So as output comes from the program, the select statement will see that there's output available and decide to pick that output to run, and it will update the data, and it won't have to lock it. An event will come from the front end in there that will modify the data in some way. And that data will be stored, and the select statement will see that and pick that one and work on that data right here, do the updates, and then there will be something that says, oh, there's some input that's available, and so the select statement will pick that input and send it to the program, right? And the difference is, right, you have this program doing its own thing and this TUI doing its own thing. They're all sending like quote unquote events or triggers to this select statement that are saying, hey, I have something I want to do with this data. Can it be my turn? And it's the select statement's job to say, yes, I'm going to work on the output that came from here, or I'm going to work on the event that came from here, or I'm going to work on sending input to the program. It's the select statement itself that's making that. So you can think of like the select statement as like the quote unquote replacement for the lock. How many times have I done this in this video? Put your guess down below. It feels like I've used that a lot. I will try not to use it anymore. But again, the idea is the select statement is the thing that's doing like the locking of the data. It's ensuring that the data is consistent at any moment in time. And the reason it can do that is because this is all happening in one thread, right? So this thread is doing its own thing, this thread is doing its own thing, and they're all sending events, right? And events are coming this way, and it's the select statement that's picking how to and when to update the data. And it turns out that this is a really cool way. This is why a lot of people are big fans of Go, even though Go doesn't specifically say it's asynchronous. I did it again, man. How many times am I going to do this? Even though Go is like asynchronous, it doesn't specifically say asynchronous. It really is, right? Those Go routines are doing their own thing, and you're using channels to communicate between the different Go routines. That is an asynchronous process, right? Is when one's waiting for data, it will say, okay, I'm waiting, and it will go wait for until something is ready, and then the Go runtime itself, much like Tokyo, will know when one thread's waiting for data, or like one Go routine is waiting for data, and another one is sending data, and it will see, oh, I'm sending data to this one, and so now, this one sent it, now this one's available, and it will choose which ones to run based on what's available to it. Tokyo's doing the same thing in Rust, And so if you're familiar with Go, this kind of model won't be weird. In fact, Go has a select statement where you select on channels, and you can really think of these as channels, right? I haven't talked about much about this timeout, and this is really just for the TUI, for that front end. If you didn't have a front end that you wanted to like display data and you wanted it to feel responsive, there'd be no need for a timeout. But if all of these events are processing and none of them are actually, or I should say, if all of the events are awaiting for something to happen, and there's nothing ready for it to do it, this little timeout will come in and it will say, oh, nothing has happened in some amount of time, so I'm going to re-render the UI so it looks okay. That usually won't be the case, but if you want it to be responsive, this timeout thing happens a lot. You'll also see this in game programming with loops, right? Is like, it kind, you have these cycles of a game loop where you like receive input, handle the output, and redraw the frame, and you do that over and over again. You don't want to get stuck on receive input or whatever. So if it's not there, don't process any. It doesn't quite work this way always, depending on the language you use, but the general idea is you'll have some timeouts around these loops. And this select can be thought of as like a main loop of a program, right? It's doing that select stuff to do that work, to do all the work. Okay, so given that, let's just look at the code in the program. We've talked about all this stuff. Let's kind of review what's going on. Obviously, because we have like a grid system, especially for part 1, we want to know where we are on those grid systems. So I've created a point structure where I have my XY coordinates. I'm also using clap to differentiate between part 1 and part 2 in the GUI. It's not really, I don't really use much of it. It's really just in the main program where I say, hey, for part 1, you know, if they selected part 1 for the arg, do part 1, so on and so forth. Again, just to review, because it's been a couple months for me, you know, we're using Tokyo, which is an asynchronous runtime for Rust. I think I have previous videos about that, so feel free to check them out. Or again, if you have questions about it, feel free to ask. All of the parts happen to have a similar thing where you run the program. And we've worked with our channel senders and receivers before. Those are like abstractions over sending and receiving, but they allow us to like see what's waiting, what's buffered. And so I wrote this little helper function called run program that will give you the sender and receiver, so you can send output to the program and you can receive, or you can send input to the program and receive output. That's what you'll get. But otherwise, they're the same, right? So we create these 2 channels, and then we spawn a process. Remember, so this is, you can think about it like a thread, but it's a lightweight thread, right? We're going to spawn it's more like a Go routine, right? We're going to spawn a process, and what is that? Is we're just going to create our Intcode program, our Intcode Computer, with our given input using the input and output of our channels. And then before we hit run, we're going to update the memory if we're on part 2. That was one thing I don't think I mentioned, but it says it here in the thing is, for part 1, you initially just get a map. That's all you get. It spits out a map and then it quits. And so your idea is to read the map, find the intersections. For part 2, you're going to update a memory setting. You're going to update the initial memory address 0 from a 1 to a 2, and that will trigger like part 2 of the Intcode program, and it will then create an kind of an ASCII terminal. It will output little things that will say, hey, what's your main function and what's function A, and so on and so forth. And then you'll input that information, and then it will run that for you, and then it will ask you, hey, do you want a continuous feed to see what's happening, right, with the program. So in my code here, you can say, oh, if I'm at part 2 or the GUI, I want to update that memory, and then I want to run it. So this is just a helper function. They all use the same one. You just tell it what part you're on, and it will update the memory if you need to. Not really much to that one, but it is the core part. Like when we're looking here, this part right here kind of is all encapsulated in that, right? It's going to give you the channel for output and the channel for input, like these two right here. And then all of this is happening inside that function right here, right? We run it, and then we have our inputs and outputs we give it, and all of that happens within this spawned process, and it just continually runs until it's done, right? So how does it look for part one? We spawn it running. We aren't interested in input, but we will be receiving output. And for if you remember what happens in part one, you're really just asking, can I find these intersections? So my thinking was, well, I'm really only interested in the hashes. And then once I've found all the hashes, I can say to myself, where do they intersect? And then I can sum up the excuse me, the product of the XY coordinates. So that's what I do. I kind of start at XY0. I create a hash set to track them. If I ever get a hash, I know I should insert that hash into my grid. And then I just need to know if I hit a 10, which is a new line, I'm now incrementing my Y location and resetting my X. So you can think about what's happening there is when I hit here, the next instruction I'll get is a 10, which is a new line, and that means I should start right here. My next position will be right here, the next thing I get out. So that's what I do. I just loop through that, and eventually I'll get all of the hashes into my grid right here. And then what I can do is I can just iterate through that grid, right? As I can say, for each of the items in the grid, do I have an equivalent? Do I have a hash in each of my, other coordinates, or to above and below and left and right of me? So if I'm right here, I want to check here, 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 and here. If they're all hashes, then I know this is it, and I can do my math, right? I can add that to my part one, which again is just the product of those two things, and I'm summing all of those together. So for example, right here, obviously this one would not be it because, it has dots around it and not hashes. And really, I use contains because it won't be there. The dots won't be there because I'm only worried about the hashes for part one. I guess I can just show you really quick how it looks, maybe. I run part one and it spits out the answer. It does it relatively fast, right? There's not much to this. Again, I'm just running the program, reading the output of the program and storing the hashes in a grid. And then I'm iterating over all those items in the grid, seeing if it's an intersection, meaning they have points all around them, or hashes all around them, and then just incrementing my solution till I do it. Part two is not much harder. Once you've figured out the solution, you run the program, and then you spawn another process to send your results, and you just keep doing that until you get some output that's greater than 255, and that's your solution, right? Again, it says here in part two, once you've figured it out and you've gone through all the things, it will eventually spit out some non-ASCII value way above the ASCII at range of ASCII characters, and that will be your answer to your puzzle, right? So that's what I do here. Is it's kind of a little of a shortcut, but I'm just saying I'm just going to loop through all the output until I get one that's greater than 255, and that will be my answer, and now I'm done. So the real question, though, is how do you get this? Well, maybe I should show you really quick what, here's my solution to part two. And you can see it runs, again, pretty fast, and it spits out the correct answer, right? Okay, so you're like, well, how do you solve part two? And that's, for me, where the GUI comes into play, right? So you can potentially have this GUI right here, and it's going to ask you, it's going to say, hey, what do you want? How do you want it to work? And this is where you can do the trial and error, right? And so you're trying different things. You'll say, oh, if I do A, B, B, A, C, A, C, A, C, B. Sorry, if you notice I'm looking, this was me dorking around and like writing down the answer that I got. So yours will be different, right? But you're trying these things out. R8, R12, L12, and then C was R12, L12, L4, L4. Continuous feed, yes. So we'll do a yes so you can watch it right here. But you can see what it's doing is on the left-hand side, it's actually saying, hey, what do you want your main program to be? What do you want function A, B, and C to be? And you play with those. At least that's what I did. I played with them and I said, oh, well, you know, I can see this pattern right here that goes kind of like this way, this way, this way, and this way. That also shows up, I think it's right here, this way, this way, this way, this way, this way. Is that right? Oh no, like right here is another one where it kind of goes like this and this, this, this. That one happens to show up like right here. I think that's the one that one was duplicated, right? So there's just these patterns. I think the first pattern is just here, here, and here. And that one shows up, for example, like, right. Where does it show up? A, B, B. Oh, I think it's right here. Anyway, oh, right here. Now I can't. Oh, here. Nope. Here. Yes, here. Like right here, right? And you start to see these patterns, right, of where it's going. Oh, okay, mine reached the end and it spat out the dust. But this was me. That's how I solved it, is I just played with this. And it took several tries, right? Is like some of them I'm like, well, I can see like, I think the first time I did it, like I was doing this and this and this and this, because that's over here somewhere. But it turned out it's easier if you do it the other way, or if you just do from here to up here to here. You can do that in a few places. How many times? 4 in total. And then I think the key to mine was actually the C solution, this R12, L12, L4, L4, which is like right here. You go, where can I find one? Like this one right here. You go 4, 4, 12, 12. Finding that one, and then I think this one right here, where you're like 4, 4, 12. No. Is it right here? Yeah, 12, 12, 4, 4. So like finding this little hook in those two places meant that I could do A's and B's. Like the B was like the nice one that kind of solved the rest of them. So you can see A's and B's are like all over the place, and those two C's. So I've talked about this a lot, but that is the GUI, right? So the real question is, and so this is the way I felt comfortable solving it, is creating a GUI, kind of playing with it until I solved it, and then using that to solve part B. And so, or part 2. And so you can see part 2 is I'm basically like, here's the input I want to spit out, and I just spawn a process that sends those repeatedly. And then I spawn another process, or spawn another, Tokyo Go routine, whatever, that is running part 2. And those two things are interacting with each other to do that, right? But how does the GUI work, I think, is an interesting question. I won't go too much into this other code, right? I have some states that track where I'm at in the UI, and I have the TUI code that is down here after my handler functions that are actually doing the drawing. We've talked about Ratatui before, and I think just a couple weeks ago, Ratatouille actually got some funding to do some really cool enhancements and stuff like that. So TUI is a really cool thing. Again, I won't go how it's drawn, but we talked about that a little bit. But you can see here, I kind of have like a terminal on the left-hand side and then the grid on the right-hand side here. And you can see how all that stuff is drawn in this code below here. What I actually want to focus on is the select part of it, right? Like that's the key thing is understanding is I'm going to have some app state, which is this right here, where I have my grid, I have my terminal output, I have the current line I'm typing. I wanted backspace to work, right? So I could, oh, I made a typo. And so I have my current line that's visible. And then I have my, my output state, which is like, uh, in the grid, you'll actually be switching between things, right? The initial time, it's going to give you this grid on the, how should I say this? The program is initially going to give you the grid, and then it's going to go over here to the terminal where it wants you to type, and then it's going to go back to the grid, and it's going to print it out. It's going to give you the whole grid, and then it's going to give you the whole grid again as this little thing is updating. You notice as when I put the continuous feed yes, is it would spit out the updated grid every time it moved, right? It wouldn't just tell you a new location, it would spit out the grid again. So I had these output states that were used to kind of tell you, where are you? Are you drawing the grid? Is the game over? Are you in the question loop where you're going to be reading from memory? Those type of things. But all of this is, again, this is the app state, right? And what I want is for that main select thread to be the only thing that modifies that state. So all of the other programs can tell me how to update it via, communicating with this main select thread. But they'll be doing their own thing in their own spawn process. Again, if I show you what it looks like, I will get there. Okay. So you can think about this spawned process over here, this spawned process over here, and then you have this little, process right here, which is like the main thread. All of these are doing their own things, and they're sending events and or receiving events from this main select thread. But it's only this main process right here that is updating the app data for these things to view and to use. So how does that look? I tried to simplify it in the select statement. Let me get there really quick. Okay, it's right here. So here's the TUI. When you call run TUI, what does it do? Excuse me. We create a new TUI. We initialize it. This is like setting up the terminal. We start the program running. And remember, it spawns its own process. It spawns its own Tokyo process. I should get that terminology right. I don't remember what it is. I'll have to go look it up after. But then I just create my app state. I create my reader for my handling input from the TUI. And then I want to track all those inputs, right? But otherwise, I'm just going to loop until I'm done, right? I'm going to loop forever until I quit. There's a are you done thing somewhere in here. Yeah, right here we break if things are done. And I'm just going to call this select function, right? And it looks a little different than if you're familiar with Go and the select statement, but it's largely the same. I guess what I should say is it works the same way. This looks more rusty, and the Go ones look more Go-like, right? So you can see here, this is all I'm doing is I'm saying, hey, if I receive output from the program and I'm not done, I should handle that output. If I receive an event from the event reader, right? So I'm typing on the keyboard, I should handle that event. And if I have something to write, I should try and write on it. I did create this helper function called write or wait. Let me go there and show you what it looks like. The idea behind this write or wait is, like in Go, if you have nothing to write on your select statement, like if you don't have anything you want to push to the channel, you kind of have this similar problem, right? Is like, I don't have any data to write, so I'm not going to write anything to it. You want to, but I still want that to be in my main select loop. Is I want to say, hey, I want to write, but if I don't have anything right, I just want to wait forever. And Rust Tokyo in particular has a way of doing that. Is you can mark it as pending. So what happens is this write or wait is an asynchronous function, and if there is some value to send, I will try and send it. If there's not, I will just issue this pending await, and this never returns. And that's, you kind of handle it the same way in Go, is if something's never going to generate a value, never going to send on it, right? If you're not sending anything on the channel, it just assumes, okay, that channel's not in contention for my current select statement, right? And so this is the way to do it in Rust, is at least the way that I found, is I'm going to have some value that I want to send, and if there is an actual value, if it's something, try and send it. If not, just send back a pending, which will like never actually return. So that was so that's what this write or wait is. Basically saying, if I have something to write, so if my input is not empty, that I need to send is not empty, try that. Otherwise, just block. And then finally, I have this sleep, which is the timeout that I was talking about right here. So that previous one was this event handling, and this one is the timeout. And then the first one was handling the input and output of the actual program. But all of them, what they do is, I tried to minimize like the size of the select loop. Some people actually like all of the information to be in the select loop because it makes it clear what's happening. I used functions to try and make it clear that I'm really only doing 4 things in this select statement, right? Is there output? Is there an event to handle? Can I write something to the Intcode computer? Or should I time out, right? Those are really the only things that we're asking. And then, so after we do that select, we draw the app, right? These handlers right here, handle output, handle input, and these write or waits, they've done something to the app state, right? I guess it's primarily just these two have done something to the app state. And so at that point, we want to update what's happened to it, right? And so we do that. And we just loop and loop forever and ever, handling those things in the select statement, handling that data until we've solved it. And for me, again, I think I've talked about this before. Historically, the whole idea of like selecting and polling is traditionally what's used in like C, like using epoll and stuff like that. I think these things are really cool. They're a way for you to say, yes, I have a lot of threads. Yes, I have a lot of them that wanting to do stuff, but not all of them want to do stuff at the same time. There's going to be interactions with them. And the coolness of that factor further came with like Go, right? Is the ability to have these channels interacting with each other. And again, this is like not necessarily new stuff, right? We've been doing epoll for decades. Even before that, the people that wrote like the high level things of like this interprocess communication, there's a white paper on it. That was, 50, 60 years ago. I guess I don't know exactly how long. Very, very long ago, before I was born, right? So this stuff has been around for a while, but once you've got it figured out in your head, I think this looks very readable. That's why I like it. You do have this weird, right? Suddenly everything is async, and so you have to do a lot of, you're putting dot await all over the place. You're putting, dot receives, your await unwrap, these things. It really changes the way your code works. But I think once you understand the nature of asynchronous programming, it can be very powerful. And so that's why I wanted to show it here, right? Is I'm actually doing quite a lot, right? There's a lot of interacting going on in this program, but it's boiled down to these removing comments, 15 or 20 lines of code. Now, what I do with the handle output and the handle input, that there's some complexity in that, right? So if we look at the handle input, for example, you can see there's a bunch of stuff, right? Where I say, well, if I hit Q plus control, I should quit, right? If my output is done, I shouldn't change the output state or the app state. Otherwise, handle, if I'm in the question loop and I hit backspace, I should, pop items off what I was typing. If I hit enter, I should assume that's like a new line in the state, right? So I've had to think those things through, but this is very like, how do I say this? This stuff that I'm doing right here is very simplistic, right? You can just reason about, okay, well, what's all the input I could receive? What are all the input values that I could receive? And I'll just have cases for all of those things, right? And most of them, all of them can be handled in 5 or 6 cases, not super complicated, right? The same thing with the handling output, right? I know if the value I get is greater than 255, I've gotten the dust, and so I can finish the program. Otherwise, I just need to check, right? Is like, am I in the question loop? Am I in the redraw loop? And if I'm in the redraw group, where am I like in the grid state? These are things that I have to think about. And I could talk about this stuff a little bit more if you guys are interested in. But it was mostly just hey, I just need to track the output and the last output and my current state. And based on those 3 values, and I can figure out what I need to do next, right? And so this looks a little bit like if you're familiar with finite state machines and stuff like that. This code looks a little bit like that using the match operator, but it's not really that complex, right? As you say to yourself, okay, well, if I get 2 new lines and I'm in the redraw grid, that's where what's happened in that part of the program is it's drawn this whole grid on the right hand side here, and now so I get a new line and then I get a second new line. It means I'm starting back up again at the top, right? You could potentially, if you knew the grid size, you could say, oh, I reached the end, so I know I go to the top. But for me, it was just as easy to say, okay, well, if I get 2 new lines in a row, I know I need to redraw, and so I set my X and Y's to the different value, right? If I'm in the redraw and I get a new line, now I know I've updated my Y. And then for all other cases, if I'm in the redraw or the init grid, I'm going to be updating my grid value, right? So this is my actual app state. I'm saying, okay, I know I need to put that value in the grid, and it's either going to be a dot or a hash or a position of the vacuum, right? Anyway, this is just kind of, I guess, the point I'm trying to make in all this is saying these things these parts aren't too tough to reason about. Maybe there's some difficulty. I know finite state machines can be a little tough to reason about, but when you just think about it's like, oh, I just have my output, my previous output, and my current state, I can figure out what to do there. That's not too hard to do. What's really hard is how do you do this like inter-process communication? And again, it's not truly inter-process, but you can think of it that way, right? Is we have an Intcode computer that's running. We have a TUI that has input and output events to handle. And how do you get those 2 things to interact with each other? Again, you can do this with locking mechanisms, right? So we could potentially have an app state like this that has a lock around it, that when we say, hey, it will have a function that says like, here's some output, and it will do a lock and handle that output and then process it. And that still works, but it's you definitely have to be careful of how you're locking and when you're not locking, so you're not getting yourself into a deadlock or anything like that. But it does feel, to me at least, like this select type thing is super clean when it comes to this inter-process style communication. That's just you'll see this is why I think Go is super popular in the cloud environments and Kubernetes and those type of things, is because those interactions can be very complex, but you can simplify it by thinking along these high level things, right? Is like, hey, if I just select on all these events and update some state based on all those events coming in, or communicate between those things between those processes with these select statements, I can get a lot done, right? And I can reason about it more easily than the other way I used to. So there you go. That's my solution. I thought it was fun. I had a lot of fun doing it. Again, I think the key things to take away from this is if you're trying to learn how to program or learn how to do it, try it some different ways. I went with the asynchronous approach because I felt like it lent itself to how we've been doing our Intcode programming in the past. Some of the problems that come up, I think I started working on the next one, and it wasn't that tough because we'd already done a lot of this stuff. So we'll see how those future videos work. But I think, if you're working on this day, you can solve it pretty quickly just by, once you've got your program working. Part one and part two aren't that tough to solve. So take it a step further and say, hey, can I build a UI to show it off? Can I, use asynchronous programming to turn my program and my TUI into like communication devices that can interact with each other via this select statement, and that will get you a long ways. Um, and just in conclusion, very grateful for everyone and all of the interactions you've had with me. I'd love to hear what you have to say down below. Do you have another way that you solved it? Maybe you used AI. Maybe you used, kind of a breadth first search, or some kind of solution where you like try different ways until you find optimal paths to get to the solution. I definitely think those ways are doable, and I'd be interested to see how you did that. For me, it felt like a fun way to. I've been doing Ratatouille, and I've really enjoyed it. We've talked a lot about Tokyo, and so it felt like building a little GUI to show that off would be the best way to do it. But again, I would love to see your solutions. I know you can't always post links in the comments, but obviously I will have all my code in the description, and feel free to just share with me other ways of. I'm sure you can find creative ways of helping me find your code. I'd love to see it. So, with that said, that was day 17. Was it day 17 of the Intcode programs for 2019? And I hope you enjoyed it, and we'll talk to you next time.